Okay, we're going to talk about homogeneous aqueous systems today in this section. And I don't know if you've ever seen this, but you can grab a dill pickle, put two different kinds of electrodes, an iron or copper electrodes in the ends, and you can light up a pickle. So I thought I'd show you that. So some solutions can have electricity run through them. We'll talk about that. So we're going to talk about making solutions, and a really simple example is Kool-Aid. So Kool-Aid has the Kool-Aid powder, that's the solute, and the solvent is the water. We can have lots of different solutions, but that's a really simple one to think about. Aqueous means a solution is in water, and so Kool-Aid is an aqueous solution. It contains the dissolved Kool-Aid particles. The solvent is the water, that's dissolving the Kool-Aid, and the solute is the Kool-Aid part. So a solvent dissolves the solute, and the solute becomes dispersed in the solvent. And we can have solutes and solvents that are all different phases. You can have all different phases. For example, if you wear jewelry, you might wear sterling silver jewelry or gold jewelry, and those are actually solutions of two solids together. So solute particles can be atoms, ions, or molecules. You could have several gases together. The air you're breathing is a solution of many gases. So we can have solutes and solvents forming all different types of solutions. When you filter solution through filter paper, both of the parts will pass through the filter. So these pieces are really, really small. So what happens when we make a solution? The solute ions break away from the crystal if they're ions, or if they're like sugar molecules, will also break away from the crystal, and they'll be surrounded by the solvent. So an ionic crystal can dissolve because they are going to break apart from their crystal structure and be surrounded by solvent molecules, and generally that's water. But we can also have molecules that will that are water soluble that will dissolve in water. So sugar is an example. Kool-Aid, the sugar and Kool-Aid particles will dissolve in the water. When we have those ionic solids breaking into pieces and being surrounded by water, it's called solvation. It's a fancy word for just dissolving. And here's an example. We have the surface of the ionic solid. Say, for example, we have table salt, Na plus and Cl minuses in a crystal shape. We've talked about that before. And then water will come in, and remember it has a negative side, partially negative side and a partially positive side. So it'll be attracted to this positive little ion, and it'll pull it away from the crystal and then surround it in the water phase, like that. So that this right here is called a solvated ion. So polar solvents such as water can dissolve ionic compounds and polar compounds. Nonpolar, like gasoline, dissolve nonpolar compounds like oils and greases. So that's why if you get oil in your hands, you want to get it off, you can go grab a little bit of gasoline and rub your hand with a rag, and the gasoline and the oil will come off. So oil and water don't mix. So we have to have the right solvent for the right solute. So changing topics a little bit, ionic compounds like the salt we were talking about are called electrolytes because, like the pickle, the pickle juice has negative and positive ions in it, and it will allow electricity to run through it. So electrolyte is a compound that lets electric current go through it in aqueous or in molten state. That means where you have a solid and you heat it up. So all ionic compounds are electrolytes because they dissociate into ions. So electrolyte means electricity will run through it. If you have a strong electrolyte, sodium chloride is a strong electrolyte because it breaks into pieces really readily in water, and you can let electricity run through it. So that's why we don't want to get hit by electricity, because our body's full of electrolytes, and it will let the electricity run through your body and hurt you. So strong electrolytes will totally dissolve in the solvent, and you'll have ions in the solution, and electricity can run through that. A weak electrolyte only lets some electricity go through. So the molecules don't totally break apart. There's not very much negative and positive charge in there. So those are weak electrolytes. And things that do not dissolve and form ions are non-electrolytes. So how do you write the formula for a hydrate? Hydrates are something that we may do in lab where we have water attached to another molecule. So a compound that contains water of hydration is called a hydrate. And this is a common lab we do in chemistry, where we write the formula, we write a dot, and then we write the number of waters that are associated with that molecule. So for example, this is copper sulfate, pentahydrate. So this is the blue copper sulfate. It's also got water attached around this. 5 waters are attached around this molecule right here, that formula. And if we heat it up, we can break the water off of it, and the water will go out in water vapor, and then we'll have the white copper sulfate left. So this is the change, is a chemical reaction. We have actually broken that bonding between the copper sulfate and the water, and the water is going out in a vapor. We can't see it, but we're left with just the copper sulfate. So this is a really common lab you'll do in chemistry, where you'll take a hydrate, you will weigh it beforehand, you will do the lab where you heat it up in a Bunsen burner, and then you'll weigh it afterwards and find out how much water was removed, and then you'll try to figure out the formula for the original compound. Sometimes we don't tell you this beginning relationship, and you have to find it in the lab. So that's called a hydrate lab, and that's a really common lab in chemistry. So some compounds can add water to themselves from moist air and make a new compound with the hydrated water there. So this is cobalt 2 chloride hexahydrate. 6 waters are associated with it. So here's some different hydrates, and you may have to do this in a lab where you get a particular hydrate and you heat it in the Bunsen burner, and then you weigh the after product and see how much water was lost. Sometimes if a hydrate has a vapor pressure higher than the pressure of water vapor in the air, the hydrate will lose its water of hydration, or effloresce. So some hydrates will lose water, some will gain water. Hygroscopic hydrates are something that like to grab water from the air, and so we use this in the laboratory. If we want to keep things really dry, we'll put it in with this hygroscopic hydrate. It will grab the water off of the material and keep the material that we want to have really dry. It will keep it nice and dry. So you might see something called dry right in the lab, where we have it in a closed glass container, and it is able to keep things really dry that way. So to figure out the percent water in those hydrates, we take the mass of water, divide that by the mass of the hydrate, and multiply by 100%, and that gives you the percent water in that molecule. And sometimes you'll do this in a lab. So if we wanted to find the percent water in this compound, this is sodium carbonate decahydrate, 10 waters, deca. We will take the formula and we'll figure out the mass of the hydrate, and then we'll just take the water mass, the 10 waters on top, and then multiply by 100. So we're going to have 10 moles of water. Each water is 18, so 18 times 10 will go here, and then we'll figure out the mass of this big giant long guy, put it right there, and then multiply by 100. So the mass of 10 waters, 18 for each one, but there's 10, so that's 180 grams. The molar mass of this big old guy is 286, so we're going to take the 180 grams divided by 286 for the total, times 100 gives us 62% of this molecule is water weight. That's percent water. So sometimes you do that in the lab. You could try this one yourself, and then you can go online and figure out and ask what the percent % by mass of water is, and see if you get the answer right. So some compounds can remove water from the air, and when they do, they become like solutions. It's really crazy in the lab. Sometimes you'll open up a bottle of a chemical, and it went from solid to a liquid because it grabs all the moisture from the air. It's really weird. So sodium hydroxide will do that, and we use sodium hydroxide a lot. And usually it's in little pellets like this. If you leave it in the air, and the air is very humid, it's going to grab the water from the air and start dissolving right there. Deliquescent, fancy word. And so a solution will form over time from the water in the air reacting with the sodium hydroxide, which is a very strong base. So let's see how much you got from this one. So choose the correct words, pause me, and then let's see what the right answer is. Okay, here's the answer. Solute and solvent. That's how we make a solution. Okay, next one. In a solution process, pause me, think about it, and come back. Alright, the answer is positive and negative ions are surrounded by the solvent molecules in solution. Last one. Ionic compounds are electrolytes because they, pause me and I'll give you the answer. Alright, they change into ions in the aqueous or molten state. Okay, I hope you learned a little bit about solutions. We're going to use it a lot and do math on it as well. So I hope you learned a bunch from this. Talk to you soon. Bye-bye.